So again, my name is Steve Lorello. I'm the .NET developer advocate here at Vonage, and I'm going to be presenting to you a brief introduction in computer vision, and we're going to be using .NET for that. So of all the topics in computing, like I said, computer vision is probably my favorite. With it, we get to take a set of fairly abstract mathematical concepts and apply them to something that's really useful and powerful. Now, if you've ever dabbled in raw computer vision techniques, you're probably like me. You probably mostly use Python or C++ or maybe MATLAB. Now, all these are really useful for sure, but they can actually be potentially limiting in what they allow you to do on the client side. And that's why I'm really excited to talk to you about this topic in .NET. So a good place to start is to ask the question, what is computer vision? And to answer that, I'm actually going to borrow a quote that my computer vision professor in grad school borrowed from another computer vision researcher. So the goal of computer vision is to write computer programs that interpret images. Now, there are two concepts that we need to unpack here. First, what are we interpreting? And then maybe more importantly, what is a digital image? So now here's a bit of an agenda of what we're going to be covering here. First, we're going to be tackling that existential question. What is a digital image? Then we'll be looking at a little bit of Hello World code using OpenCV and .NET. Then we're going to start diving into that interpreting part of our definition. We'll look at convolution and edge detection. Next, we'll actually be looking at face detection, and then we'll be doing some real-time face detection using Vonage's video API. And then finally, we're going to do some feature detection, feature tracking, and some image projection. So for our first question, what is a digital image? Now, here's an image of my muse for this presentation, my dog Zero. You might want to get used to him. You're going to be seeing quite a bit of him. So what is a digital image? An image at its most basic form is a function. And that function denotes a quantized set of intensity values by position on a two-dimensional grid. Those intensity values, which you might know as pixels, are just light intensities along arbitrary ranges. For example, a range of a byte, 0 to 255. Now, there's no rule that actually says they have to fall in that range, 0 to 255. It's just convention. And oftentimes when we're looking at grayscale images, those numbers will be on the range of -1 to 1, or sometimes 0 to 1. But technically, as long as these values can be found along a bounded range, the math will still hold. And actually, when you get into other applications of image processing, like HDR, the range of values is exponentially larger and technically infinite. Now, that image of 0 we just saw, at its most basic form, is a matrix of size n by m by 3, where n is the height and m is the width, and 3 is the number of channels. Now, a channel for our purposes here is just a light intensity for a particular color. But when we're talking here, we're talking red, green, and blue. So this image of a pepper is a classic example for looking at an image as a function in a one-dimensional space. Grayscale makes things a lot easier to think about, but the math does abstract out to any number of channels. For example, RGB, red, green, blue. And that's actually not, you could have more than 3 channels. You could have as many as you want, kind of. Now take a look at the red line that's drawn through this pepper. You could actually think of that line as its own image, which is only one dimension. And that image is denotes the intensity values on this graph on the right, with the darker spots having lower light intensity and the lighter spots having greater light intensity. Now this insight becomes really powerful, and we'll actually be seeing later how it's applied. But I want you to think very briefly, where are the edges in this image? Are they in this one-dimensional image? Are they at the peaks, or are they at the valleys, or are they somewhere in between? So now we'll be taking a look at the crux of this talk, using computer vision in .NET. So in this talk, I'm going to be using OpenCV, which stands for Open Source Computer Vision Library. As the name suggests, it's an open source tool, and it does have pretty wide adaptation. There are other tools that do essentially the same thing, that OpenCV does. For example, MATLAB, Octave, both have a lot of image processing functionality, but I like OpenCV as, for the most part, it's free. The documents are pretty user-friendly, and they'll actually explain all the math and all the insights behind every function, in addition to teaching you how to use them. Now, mGooCV is the .NET OpenCV wrapper that we'll be using, and it's widely available for the .NET framework and enables you to do quite a lot. And there is, for the most part, a one-to-one mapping between OpenCV and mGooCV. So most things that you can do with OpenCV, you can actually accomplish with mGoo. I will note that if you're like me and you're used to using the Python OpenCV library, assuming you've ever used it before, you might need a little bit of time to adjust to OpenCV, as it's much closer to the original C++ implementation of OpenCV. And just a note, mGoo does use a dual open source and commercial license. So you're fine to use it for like demos and like anything that's open source, but anything that you're using for commercial advantage, you would have to contact them to get a license. Now, to actually use OpenCV, we're just going to create a new project. For now, we're going to be creating a basic .NET Core console app in Visual Studio, where I have on my end. And then we're going to install mGooCV, the mGooCV runtime package manager. And you can install this for whichever platform that you're on. I'm on Windows, for example. Now, let's add a little bit of code to Now, remember, now think about this. mGooCV is structured around a set of static functions in the class CV invoke. And here we're actually using 3 of them. Note, I've stored an image under my resources directory named 0.jpg. That file is meant to be copied down to the build directory when I run. Thus, I'm just assuming that it's going to be there. So this first line of code here actually takes the image of 0 and reads it into a matrix. And as you're doing this, there's 2 things you really need to note. The matrices are by default read into the BGR, blue, green, red space, rather than the RGB space that you might be used to. And that's just convention in OpenCV. All these structures, so this mat structure that this thing generates, uses the iDisposable pattern. Thus, if you want to limit the scope that the memory is being used, you can use either a using statement or you can explicitly call disposed on the structure to clean it up. But if you don't, the garbage collector, once it determines that the object no longer has a reference to it, will simply call the dispose function, and that'll actually free you from the need to do anything. So the second line here creates a window with a title provided to it. And that window will actually display the image that's provided by the second argument into that window. And the final line is a wait key line. And this is similar to console input. It just waits for you to press any key while you're focused on the window. And without this, the image would actually disappear before you got to see anything. So here's the result of that little program. When you run it as a console app, it creates a window and shows up with 0 lounging around the house. Now, the next topic I want to cover is convolution. Convolution is the process of combining 2 functions to produce a third. When we're working with images, that generally means taking a large matrix, which is our image, and running a small matrix, a filter or a kernel, over it to produce a third matrix called a feature image. And that's actually where we're going to see a lot of our insights. So this is essentially what's happening here. Notice the shaded region of the image, the blue matrix. It's the same size as the filter or kernel that's being run over it. That's because this 3x3 submatrix of our image is going to be dotted against the filter to produce the feature in the final feature image right here. Now, running this operation successively over the entire image will produce a full feature image for us. And typically when we're done filtering, so we're done running this thing over the whole thing, we're actually going to divide the feature image by the sum of this kernel to produce a final output image. So like this 51 here would be 4. So now I'd like to illustrate why convolution is such a powerful tool when we're thinking about computer vision. We can do some really neat things with it. And to accomplish that, we only really need to tune the kernel that we're using. So this kernel right here is called the Sobel operator. The Sobel operator enables you to do something very critical. edge detection. Recall that pepper image that we looked at before. Remember when I asked you, where are the edges, in the peaks, in the valleys, or somewhere in between? Well, the correct answer is actually in between. If you at some point took or can recall calculus from your schooling, you might remember something called a derivative. A derivative is simply the rate of change between 2 points in a function. It's a slope. And it's the derivatives that the Sobel operator is going to calculate for each pixel in our image. Remember how I said that convolution is combining two functions or images to produce a third? Well, that's exactly what we're doing here. We're combining our input image and our kernel to show an image showing the magnitude of the derivatives for all of the pixels in the image. Those derivatives are sometimes more clearly referred to as the edges of the image. Now, there are two commonly used Sobel operators that work in concert with each other. The first one, the one on the left here, is the gradient in X operator. And the second one, the one on the right here, is the gradient in Y. And after combining these two, you actually get a third image, which is our full gradient image. So here he is again, my buddy Zero in his Mr. Rogers sweater, as I like to call it. Notice all the edges in the image. When you think about it, those edges, the places where the color is changing, is really where we're getting most of the information of the image from. The flat surfaces in the image, like the wall in the background, even the floor, they don't really tell us much between any point in that image. And really, like, I think Zero's cuteness in this image is a subjective reading of the contours and colors of the image. So now, after running convolution with a Sobel operator over our image of Zero, we're left with the gradient outlined edges of the image. Those are the parts that are very bright. Now, the operation of convolution has a wide array of applications, particularly when it comes to feature detection. And we can actually leverage this in something else that you might have heard of, convolutional neural network, which is a topic for a completely different day. So if you want to calculate the Sobel gradients from an image, here's the process. Now, I assume that all the images that I'm reading in are color images. Might be a bad assumption. At least in this case, it is a color image. So the first thing we need to do is actually convert it to a grayscale image. And that's what this first line here is doing. And note, I've already initialized this gray matrix and some of these other matrices in here. I'm just newing up essentially matrix objects. It's nothing particularly special. That's actually going to hold the output image. CVT color converts the image between the different color domains. In this case, we're going from blue, green, red to gray. The next line here is actually doing something you'll see kind of a lot of when you're looking at image processing. That's a Gaussian blur. I'll explain that next, but it's actually blurring the image, which is a good thing. The next image is, the next thing we'll do is to calculate the gradients in X and the gradients in Y. That's what these Sobel calls are doing. The arguments here are the gray image that we just got from the CVT color, the gradient X matrix and the gradient Y matrix that we're saving this into, and this depth type, which is the number type that we're storing these into. Grad X and grad Y are 16-bit shorts rather than an 8-bit unsigned integer. And then the X factor and Y factor, which is the direction in which that we're calculating this, and the gradient size, which is the square size, or the kernel size, which is the square size of the kernel. Next, we actually need to take this output and we need to scale it back into the 8-bit unsigned integer space. And that's what this convert scale absolute value is doing. Then we just take the two and we add them weighted together. And that actually produces our final output image. Now see here, the gradient image in X and the gradient image in Y. Notice how they're actually pretty different from each other. In X, the vertical lines are the most prevalent. And in Y, the horizontal lines are most prevalent. And this might actually sound contradictory to you because X is the horizontal direction, so shouldn't the horizontal lines be showing up? In fact, the vertical lines show up because they're actually the gradients that are calculated perpendicular to the running edge of the image. So X actually shows up vertical, Y actually shows up horizontal. And here again is our final result. Notice how you see both the more horizontal and vertical lines kind of showing up nicely in this image. And that gives you a pretty good idea of what's going on in the image without essentially any of the color from the input image. So now, probably the most ubiquitously used kernel is the Gaussian kernel. Lots of operations in computer vision will run what's called a Gaussian blur over an image prior to using it in other computer vision functions. So for example, that Sobel operation that we just looked at. Gaussian might sound familiar to you if you've ever taken statistics. It's just another way of saying a normal distribution or bell-shaped curve. So we start from some center mean value here. And the further you get away from that center, the less weight that we're going to provide that pixel. So here we start at 4. If we're 1 away, we drop down to 2. If we're 2 away, we drop down to 1. So one of the things that really confused me when I first started learning about computer vision was, why is blurring useful? And the reason it's useful is actually because digital camera sensors tend to have a lot of noise added to them. And even a little bit of noise can really throw off a lot of these techniques. So blurring images, which might make them less detailed to our eyes, actually helps remove that noise and enhance the clarity for our computers. So to illustrate this to you, why these kernels are so useful, I'm going to show you these 2 blurred images. So that's our Pepper image from before, and of course it's an image of Albert Einstein. Now they have some artificially added noise to them. This is not the noise from the original image. Now that noise, because it's artificially added, is obvious to our eyes, whereas noise that's straight off of a film or a camera sensor may not be so immediately obvious, but it does exist. Now, think about how our edge detector is going to work on these 2 images. Pretty poorly, you might imagine, because while there's detail that's in the images that are perceivable to the human eye, the oscillation between the pixels is just too extreme for a computer to gain meaningful insight of where the edges are. So another filter that does something really useful is called a sharpening filter. Now, a sharpening filter will tend to magnify the center pixels by weighting them, up-weighting them, and down-weighting the non-center pixels. And as I'll show next, you can actually do have the same effect by getting the detail from the blurred image, by subtracting the blurred image away from the original image. So take a look here. We're taking our Gaussian blurred image. And like we saw in our last code snippet, we're actually going to create this blurred image. And then we're going to get the detail of that image by subtracting that blurred image from the original image and then multiplying that whole sum by 2. We can then create a sharpened image by adding the detail back to the original image, and that actually produces a sharpened image for us. So see here, we're going from our original to our blurred image. Now remember, blurring makes us lose detail to our eyes, but it increases the detail for our computers and for our algorithms. And now on the left here is the detail image, which is the enhanced difference between the original and the blurred image. After adding that to the original image, we get a nicely sharpened output image. And it's actually probably easier when you're comparing apples to apples. So see here, the original versus the sharpened image is 0. You can see the differences in sharpness here. And you can tune the degree to which you multiply the detail to increase sharpness. But if you overdo it, you'll actually wash out the image and add a lot of weird artifacts to it. So if we go back here, this 2, you can bump that up to 3 or 4, whatever you want. But if you go up to something crazy like 10, you'll actually get like a lot of these weird artifacts in here. You can see like the colors kind of getting messed up as it tries to overemphasize individual pixels. So now that that's done, we're going to move on to something else that I think is really cool: face detection. Now, using OpenCV, we can actually run face detection in real time on multiple video streams. So first, we're going to discuss a technique for facial detection was developed by Paul Viola and Michael Jones, which is both really quite rapid and robust. Now, we'll be taking these little masks called hair-like features, which we'll see in a minute are just very simple little shapes. And with them and an integral image we generate from our input image, we'll determine the relative shading of different regions. And after combining a lot of these little hair-like features, we can build what's called a cascading classifier to perform our face detection. So these little hair-like features, as they're called, are simply black and white images, split into 2, 3, or sometimes 4 different rectangles. And they may look like silly little shapes, but they're actually extremely useful tools to run all sorts of detection algorithms. In particular, we're going to be looking at facial detection. Now, one or two of them aren't particularly useful for image detection, but hundreds of them applied at varying scale to the same image with a well-tuned model can actually be very robust and more importantly, it can be very, very fast. And I mean, it can run on real time on multiple video streams with low overhead fast. But wait, you might be asking yourself, you're running hundreds or thousands of these at the same time. You've summed up and subtracted all the pixels under each region at varying scales. Now, how could that possibly work performantly? And the answer to that is actually the core of the Viola-Jones algorithm, an integral image. And we thought we were done with our calculus terms. So if you took calculus at some point, or you can recall it, you might remember what an integral is. So an integral is just the area summed up under a curve in a function. And that's exactly what these are. These images represent the sum of all the pixels above and to the left of each pixel in the image. Now, what does this do for us, you might ask? Well, the hard-like features that we were looking at require us to sum up all the area under the white images and sum up all the area under the black parts of the image and find the difference between those areas. Now, each summation is an order of n by m operation, where n is the height and m is the width of the feature. Now, this might be acceptable or scalable at like one or two of these features, but this algorithm needs a lot of them to run quite robustly. And so this diagram here illustrates how the integral images makes the algorithm so much faster. To find the red rectangle, which we can think of as representing one of our hard-like features from before, we only need to take the bottom right-hand corner of our integral image, subtract it from the bottom left-hand, bottom right-hand, or top right-hand, and then add back the top left-hand corner. And that's it. Remember, we've summed everything up above and to the left of each point in our integral image. Thus, when we subtract B away, we're effectively subtracting everything away from the image that is above the feature that we're interested in. When we subtract C away, same thing for everything left of the image. And by adding A back, we're actually adding back the detail that was double negated by subtracting B and C. So with that, we can very quickly calculate the shaded regions covered by our hard-like features. And those relative shadings, along with some other ML techniques, well, we can actually build a classifier that'll swiftly and robustly detect faces in an image. Now, you might be asking yourself, how does this going to apply to our .NET program? And it's actually quite a bit simpler than even the process that I just described. We're going to OpenCV, or we're going to use OpenCV, and it actually has a large collection of these hard-like features prearranged into a model that you can use for a cascading classifier. That model is available in an XML file that can very easily be ingested into using mQCV. And with that model ingested, we can construct a cascading classifier. Then it's just as easy as running a detect method and drawing the rectangles around the faces. And this is it here. This is all you need to do to actually detect faces in .NET. We build our classifier from that input XML file. We do an imread to bring our image into a matrix. And then we actually just get these faces rectangles by running detect multiscale on the image. And for my own edification here, and I'll explain this to you in a little bit, I actually add a min size of 300 by 300 pixels. And then for each face in the faces, I just draw a rectangle on the output image. And here's the result. When it's run against an image of me, as you can see, it actually detected my face. Now, the reason why I had this 300 by 300 is this thing is so sensitive that it actually picked up the face of Roger Clemens and the face of Jorge Posada over there when I was testing this before, and I wanted to confine it down because it can detect faces, and sometimes those faces might not necessarily be live human faces, they're just representatives of those faces. Now, this method is actually quite robust at different scales of the image. Like I said, it detected Jorge Posada all the way in the background there. But it is vulnerable to lighting changes and rotations. Thus, if I tilted my head too much, it'll actually lose it. Also, note this algorithm is for facial detection and not facial recognition. There are other techniques that are way more suited to facial recognition than this. So now that we actually have gone over the basics here, we're going to take the same technique, but we're going to apply it to a real-time application just to see how powerful it is. We'll be doing this with the Vonage Video API. So we're going to actually create a WPF Windows Presentation Framework client application. We're going to add the OpenTalk client SDK to it, and we're going to add a new class implementing something called an iVideo renderer, and we're going to call that face detection video renderer. And that's going to be extending control. Control is the base class for like all the elements in WPF applications. Then we're going to add one of these to our main XAML file. That's our layout file. We're going to put it in the bottom right-hand corner, and we're going to call that publisher video. And that's actually what we're going to be detecting faces on. Then we're going to add a detect faces and connect button, and we're actually going to use those later. So now that we have the main window set up, in main XAML CS, which is like the file where like most of the entry point logic is for the GUI, we're going to construct a publisher in a session. Now, ahead of time, I actually got an API key and a session ID and a token. The API key is just tied to your Vonage Video API account in its project. The session ID is something that you can generate using Vonage's video REST API, and you can just leverage that through one of our server SDKs. And the JWT, same deal. You can generate them through a JWT. So that could all be done dynamically. I'm just hard coding them here for the sake of simplicity. Notice how I am constructing the publisher here. I'm actually passing in this publisher video. That's the face detection video renderer that we're going to be adding. We're going to be creating, and that actually has the ability to detect faces. So next, we're going to manage connecting to our video call. So when a user presses the connect button, we're going to be flipping the connection state. And it's as simple as this. On the session object that we created before, we call connect, passing in the token that I was mentioning. And then when we want to disconnect, we just unpublish our publisher's video, and then we disconnect. The next thing we're going to do is actually manage when the detect faces button is pushed. And for lack of a better term, when it's pushed, we're going to start detecting faces. And what we're doing here is we're just toggling the face detection on and off. There's a flag inside the face detection video renderer telling us whether or not to detect faces. So now this function is where we're actually going to register, our on-stream created event. So when the on-stream created, so when somebody gets added to the video call, the remote participant, we're going to create a face detection video renderer. We're going to toggle the face detection to the same state as the publisher's face detection. We're going to add that, face detection video renderer to our grid. So we're going to add it to the UI. We're going to update the grid size so it's large enough to compensate for it. We're going to build a new subscriber, and then we're going to subscribe to the incoming video stream. So now that we have that layout and the session initialization kind of up and running, we need to manage the actual real-time face detection and displaying of our boxes. So by having our face detection video renderer implement the iVideo renderer, we are going to be getting each frame that comes through a renderer. So we're going to intercept each of those frames, and we're going to run face detection on it. Then we're actually going to draw a rectangle on each frame so we see that where the face is. And finally, we're going to render the frame. So here's the beginning of our render frame function. So remember that each time our renderer gets a new frame, we're going to intercept it. So we write that frame out to a writable bitmap, and that's actually what we're going to be doing our face detection on, and it's what we're going to be drawing at the end of this. So essentially all we're doing here is creating a bitmap, and we're telling the brush, which is actually doing all the rendering for our UI, what its image source is. So like our video bitmap. And this next bit here, I'm sorry that it's a little big and kind of overly complicated. But essentially all it's doing is it's reading an image in, and then it's reducing the size of it. And the reason we reduce the size is, to make it run faster. Like I said, this is invariant to scale, so you can compress it quite a bit. I compress it to a quarter of the size, and it works quite well. Then we're going to actually add it to this concurrent stack of images, and I'll get into the way that works in a second. Then we're going to run our face detection on the faces that we detect. And then we're going to, add dirty rect here is actually drawing the rectangle on the output frame. So while this is happening, remember that was happening for every incoming frame. We have this little bit of code that's spinning on in the background. This is actually where the faces are being detected. Now notice how we start this in the thread pool up here. And the reason we do this is the other operation, because it's running and interacting with the UI, it needs to run on the main thread of the app. So we don't want to block that while we're doing our face detection, but we want to do it continuously. So we push all the images onto this concurrent stack images. In a concurrent stack, when you call this take function, we'll actually block until the collection is holding an image. It'll pop when it actually detects that an image has been added, it'll pop it off the stack and run face detection on it, assigning it to our class variable faces. This catch down here is so when you're toggling the face detection off, it's not running continuously in the background. It'll just exit out of this. Now now that we've actually detected the faces, we need to actually draw them on the rectangle, draw the rectangles on the bitmap. Note that we scaled up X and Y before. Remember, I told you we were scaling those down. Now we need to scale them back up. And I also multiply the X coordinates by this pixel point conversion. And that's because the library that I was using, for some reason, was rendering all the X's as points and all the Y's as pixels. And that gets into a whole DPI mess that's a Windows thing that no one needs to really know about unless they're actually working with video software. So for our last bit, we're actually going to be covering, oh wait, hold on. Let me actually do a demo for you first. Goodness, I jumped over myself there. So like I can actually demonstrate this right now. Now I'm going to turn my camera off here, and it might still not work because Windows is going to detect that Chrome has my camera locked up. And so it might not show my face here, but it's going to show my remote video stream when I flip on that video stream. So in here, I'm going to just light this app up. I made it over here. Yeah, you see, you can't see my video stream right now because my camera's on. And even if I do that, I probably still can't see it because it doesn't realize it's been released yet. Now I'm going to hit connect, and that's going to bring up a video call that I'm on with myself. This is my Mac over here. This is my Windows machine over here. And when I hit detect faces on it, it's actually going to detect my face pretty robustly and pretty quickly, so that you can actually see this thing running in real time. Now, I did some tests on this to see like what speed it was running at, and it was running at about 6 milliseconds a frame. So effectively, that's real time for a video call. A video call, you're usually getting at most 30 FPS. So 30 FPS translates to about one frame every 33 milliseconds, which is, oh goodness, I'm all the way at the end of my presentation, which translates to like a frame every 33 milliseconds. So it's effectively real time. So the last thing I'm going to be talking about here is feature detection, tracking, and image projection. So the first thing we need to cover is what makes a good feature. And that's actually not a subjective thing. That's something that we need a concrete definition of for our computer to understand what it's going to be looking for in images. Then we're going to use an orb detector to detect these different features. Then we're going to be using a brute force tracker to actually track these features between different images. And then we're going to finally learn a little bit about image projection. And now why are features important? Because when you're looking at frames at different angles from each other, the same image, same general image, you need to be able to correlate them if you want to do any kind of image projection or panorama. So what is a good feature? So a good feature is a section of an image that has multiple edges. And why is that? Well, think about it. If you're comparing two images to each other, you're going to be looking at a very small portion of the image for your feature. And if you're looking at that very small portion and there's no edges in the image, edges in that small neighborhood of the image, you can't correlate it to anything else in that image because it all kind of looks the same. Now, if you only have one edge running through an image, it's going to look pretty much the same at every point along this edge. So again, it's not very useful for correlating things between images. Now, if you actually look at something that's like a corner that has multiple edges running into it, that's actually something that's quite distinguishable. And that means that when we're comparing these images to each other, we can actually correlate these corners or features pretty easily. So now this bit of code here actually does the feature detection bit on one image. So what we do is we initialize this orb detector. We create a vector for key points that we're going to be looking at. We create a vector, another matrix to store the descriptors, and the descriptors are like kind of what describe the feature to OpenCV, and we're going to use those later when we're actually doing tracking between images. And then we actually call this detecting compute function on the orb detector, and that's actually going to detect features in an image. So as you can see here, when I run this again over an image of me, you get all these little corners showing up in the image. Now the highlighted bits are where multiple edges in the image are kind of coming together, and these can distinguish itself from each other, be distinguished from each other in forthcoming frames, again, using those descriptors. So the next thing we will need to do is actually correlate those features together. And to do this, we're going to use what's called a KNN, K nearest neighbors matching function in the brute force matcher. So the first thing we do is we actually add the descriptors from our first image. Then we actually call KNN match with our descriptors from our second image. And then we call this with a K equal to 1. And then for all the features that we find matches for, if the distance is lower than some arbitrary value, so I said 400 here, we actually we'll actually pick that as a match that we're going to use. And here you'll see actually two images kind of of me like tilting my head here. Actually, these are correlating them between the two images. And like you can see, this actually works pretty well. Not perfectly, but it does work pretty well. You'll see like the images moving between each other, or the key points between the images correlated. So the last topic I want to cover is actually image projection. Now, to do image projection over multiple frames of an image, we need to keep track of the features between images and build these translation matrices called homographies. I've realized I just had my camera off this whole time. To map all features, I'm sorry. We need to build these translation matrices called homographies to map the old pixels, those old pixel values, onto the new ones. So the system of equations that this sets up is actually has 8 degrees of freedom. And you don't really need to know anything about that. All that means is that you're going to need 4 matching points between 2 images to really correlate them to each other and manage to project an image onto another one. So think about all the things that you can do with a 2-dimensional image. You can move them around, which is called a translation. You can change the scale. You can rotate them. You can do what's called an affine warp, or where everything kind of remains parallel, or you could do a projection change. These translations can be generalized to a system of equations, and you don't even need to think about this whole system up here. But that's just what the system looks like. It actually condenses down to this little matrix down here, and that's actually our translation matrix, also known as a homography, to translate the original image to the plane that we want to project it on. And this last little bit of code here is just a toy example. It takes a cat picture and a picture of my face. It detects the face. It detects my face, and then it uses the points from my face as well as the 4 corners of the cat picture to build this homography. And then it uses this warp perspective function to actually cast the cat picture onto my face in the image space of the picture of me. And there you have it. That's my face replaced by a cat picture. It's a little crude, but you kind of get the point. Now, if you want to like run this on video, you can do that as well, actually, with the tools that I just set you up with the feature detection and feature tracking. You essentially are just keeping track of where you are in the image and just continually updating that homography and reprojecting the image onto it. So I really hope that you enjoy this little stroll down computer vision way. It's a giant field, and we just started to nudge the tip of the iceberg of its potential. It's a really cool field. And before I go, I just want to tell you a little bit more about me. I've been a developer for about 7 years now. I consider myself a .NET developer first, and I'd love to be the .NET. I love being the .NET developer advocate here at Vonage, and I got started working on the global positioning system, better known as GPS, and then I moved on to the air traffic control system for the UK and the US. And this is all before I got into advocacy. And on my nights and weekends, I actually spend studying computer perception at Georgia Tech. I go Yellow Jackets. You can follow me on Twitter. You can look at my blog on Dev2. I also have quite a few blog posts on the Nexmo blog, which, and you'll probably see a theme to them. I like to study, artificial intelligence and computer vision and machine learning. So you'll probably see a theme to my blog posts. It's been really awesome talking to you. So here's some resources. Pretty much everything we've seen up to this point is in GitHub somewhere, or you can find the real-time base detection sample on our blog. All right. Does anybody have any questions?
There we go. Thank you so much, Steve. That was predictably illuminating, and I am indeed much less daunted about dealing with computer vision. We are a little bit late on time, but I am just going to I'm going to pick one question, I think, from your Q&A, and then maybe you can hang out on the tables or chat later on in the day. So this question is, are there any hosted services for computer vision?
Not that I know of. CV you could just usually run in whatever client application you're building, or you can run it server side. There might be. I'm not saying there's not, but yeah, I'm not really certain.
No, that's cool. If you don't have favorites, you're not suddenly gonna rave passionately about one, then that's I feel that's all we need. Okay, fantastic. Thank you so much, Steve. This was a pleasure.
Thanks.
Now then, we're bringing